Well, good afternoon, students. We are ready to learn our next statistical test, which is the single sample t-test. Now, you'll want to print and save this handout for your records, as this is your substitute for a textbook for the class. Now, you can read here on the page that we're going to use this test when we wish to compare two population means, mu1 and mu2, and we know one of the population means, but neither population standard deviation. Now, this is what makes it different from the z-test for means. With those kinds of problems, we were given a population mean and a population standard deviation. Here, we have the mean, but we do not have the population standard deviation. Now, in psychology, we'll likely be using this type of test when we're working with a standardized questionnaire again, or with a metric that has a well-known mean. For example, your body temperature. The understood mean there is 98.6 degrees Fahrenheit. That's the typical body temperature, the resting body temperature. What is the standard deviation? That's not so widely known. So here again, we have a mean, but no standard deviation. Now, the data that we collected in class on Wednesday fits this situation perfectly. Now, recall what I did. I had 4 cards, and I randomly picked a card and held it up, and you had to guess what suit the card was. And we did that 12 times. And then you tallied how many times you were correct, so the values could range from 0 to 12. And here we see the data for the class. Now, we also reasoned that if students are just guessing, then on average the number correct should be 3. That is 12 divided by 4. Now, another way to think about that is if you're just guessing, the probability of guessing each card is 0.25, or 1 out of 4. Remember, there are 4 cards or 4 suits. Now, also, if you're just guessing, then your guesses are independent, whether you get it right or not. So we can just simply multiply 0.25 by 12, and that gives us our value of 3. So that's the expected mean. Now, what is the expected standard deviation if students are just guessing? That we don't have. So here's an instance where we have a predicted mean, or a mean under the null hypothesis, but we do not have the standard deviation given to us in the problem. So we're going to go ahead and analyze this data with a single sample t-test, and we're going to use an alpha level of 0.5. Now we go back to our handout and we can see the assumptions here. We'll talk about those later. And we can see that we write our hypotheses in the 3-valued logic form, just like we've been doing for the z-test for means. So we'll begin by setting up population number 1 here, the population of guessers. We have the mean, 3.0. We do not have the standard deviation. Population 2, that will be the population of OSU students. We're going to estimate that population mean, and then we're going to assume the 2 sigmas are the same. So here are our hypotheses. So the null hypothesis, the 2 mu's are equal, and then the 2 alternatives. And here's the one that we're going to predict, that the OSU students on average have some kind of psychic power, although it's really not clear from the problem, but we'll go ahead and make that our prediction here. Now what I did next is I entered the data, the 30 numbers, into my calculator. So let me show you that. So here I've entered the numbers into my calculator. I select my mean key, and it turns out to be exactly 3.0. So the mean for the class was exactly 3.0. Now you also want to get the standard deviation while you're here. Here are the 2 buttons on this calculator, and remember, you want the sigma n minus 1. That is the unbiased estimator of the population standard deviation, little n minus 1, just like in the formula we learned in class. So we'll select that, and we obtain 1.53. So with a sample size of 30, we have a mean of 3 and a standard deviation of 1.53, which is our estimate of the population standard deviation. So again, we return to our handout, and now we see the sampling distribution is the t-distribution. Now, as it turns out, there are an infinite number of t-distributions. It changes its shape depending upon the sample size. Now, if your sample size is low, it's a mesokurtic-looking distribution, as you can see here, but it's a little bit platykurtic. And then as your sample size increases, it becomes more and more normal-looking. So it will approach a normal curve as the number of people in the sample size grows. But with an infinite number of sampling distributions, we need to be able to jump into the right distribution. So how do we do that? How do we get into the right distribution? Well, we're going to use what's known as degrees of freedom. Degrees of freedom for the t-test, the single sample t-test, are equal to n minus 1. So we had 30 students. So n minus 1 is 30 minus 1. That gives us 29. So we have a degrees of freedom equal to 29. Now I'm going to switch over to the t-table, which is also on the website. So you'll want to download this and print it. So here we have table A2, which is the t-distribution. And you notice we have two-tailed tests and one-tailed tests. Now in class, we're always going to run two-tailed tests. So you can always just jump to this column here. And then also notice we have alpha O5 and alpha O1, the two very popular values for your P critical. We're using O5 for this problem. And then here are your degrees of freedom. So we scan down the table here until we find 29, 30 minus 1. So there's 29 degrees of freedom. And there is our T critical value. It's going to be plus or minus 2.045. Now, incidentally, if you look at the degrees of freedom for infinity, the T critical is 1.96. That's our old friend from the Z distribution. So as I said previously, as the degrees of freedom increase and approach infinity, the T distribution will approach a normal curve. So here I've sketched out the T distribution. It's a mesocritic looking distribution, and I've put O25 in one tail, O25 in the other. We're running two-tailed tests. There is our negative 2.045, positive 2.045. So here all of that stuff is summarized. Now we go back to our handout and we see the formula for the T observed. It looks a heck of a lot like the formula for the Z test for means, except notice we don't have a sigma, we use little s, which is our estimated population standard deviation. Then we'll get Cohen's effect size and the confidence interval. All of this will look very similar to the Z test for means, except we'll replace the standard deviation, the sigma, with the estimated standard deviation, little s. So let's go back to PowerPoint and work through the rest of the problem. So here's the T formula that I copied from the sheet. Here's our 3.00 from the class, minus 3, the expected population mean. Here's the standard deviation from our calculator. Take the square root, divide that by the square root of 30, and you work all of that out. Obviously, you get 0 in the numerator, so that's going to knock it out, then it's 0. So the T observed is exactly 0. So we see the value here in the sampling distribution, and as it's not in the rejection region, we fail to reject the null hypothesis. It is not statistically significant, so we conclude that the population mean for guessers is the same as the population mean for OSU students. So we go ahead and write that out in words. It appears that, contrary to expectation, the population mean correct card predictions for OSU students is equal to the population mean of people who are simply guessing the card suits. Now we'll want to go ahead and get our P observed value, our observed probability, but we'll have to use a calculator because, again, we have an infinite number of distributions that we'd have to create these sophisticated tables for. So I'm going to go to the website here, and we're going to enter in our T observed. That'll give us a probability, and we'll double it just like we've been doing, and that will give us our P observed. Before I do that, you should probably be able to guess what P observed is here, since the T observed is exactly 0. So here's the calculator, and we have 29 degrees of freedom. The T value is exactly 0, and the probability is 0.5. Now we're going to double that, so we go back to PowerPoint here. So we have our 0.5 here, multiply that by 2, and we get a P observed of 1.0. You can't get any higher than that. So again, obviously much greater than 0.05. The result is not statistically significant. We then go ahead and compute our effect size. We'll plug and chug through the formula here. 3.00, our sample mean, minus the expected mean, divided by the standard deviation we obtained from our calculators. And that, again, gives us 0 because of the numerator here. So this is a 0 effect. There's really no need for Cohen's conventions here. The two means were exactly equal. We then obtain our confidence interval. It's a 95% confidence interval building around the OSU mean. So you can see the formulas here. There's our T critical value. There is the standard error of the mean. And we plug and chug through, and we obtain 2.43 up to 3.57. So I'm 95% confident this interval includes the true population mean for OSU students. And that's about it's a 1.14 point spread. The standard deviation is 1.53, so therefore it's really middling precision. So in summary then, we do not have a significant finding. It's non-significant. So drawing an inference from this study, the statistical evidence for average psi phenomenon anyway among OSU students is simply non-existent here. The obtained mean of 3 for the OSU students was exactly equal to the mean one would expect under guessing. The standardized effect size was, of course, then equal to 0, and our confidence interval indicated reasonable precision. So overall, this would be decent evidence that OSU students, at least on average, are guessing.